Good morning, everybody, and welcome to today's webinar on 14119 interlocking devices. My name is Alec Bryce, and I'll be your presenter for this morning's webinar. And I will be joined by my co-host, Jamie Thomas, who is sitting in the background. And if you have any questions, please use the little taskbar on the right to type them in there, and he'll do his best to answer those for you during the webinar. If for whatever reason we don't get around to answering it, we will get back to you next week with the details. The webinar is being recorded, so you will receive a link to the recording, and it's available for reference on our GoToWebinar channel, so you can find it there. And if you want a copy of the slides, then just drop us a note in the question box again, so that we can get those sent out to you in the early part of next week. So what are we going to look at today? Well, as we said, it's 14119, the interlocking standard, and it's the new version that was released earlier this year, but it is titled 2024. It looks at the different types of interlocking devices. We'll talk a little bit about defeat or manipulation and overriding and measures to prevent that. Some details around the requirements for the control system, fault exclusion, fault masking, some test procedures and details that have been added in there. And finally, we'll look at the details around trapped key interlocking systems. Just as a reminder and an introduction, the standards themselves are in essence grouped into three levels, A, B, and C, in that the A-type standard is sort of specifies fundamental concepts and things like that. So, for example, EN 12100 is for risk assessment, and it gives us the iterative process of conducting a risk assessment. B-type standards deal with general issues and aspects across all types of machinery. So things like, as you see on there, 13849 for control systems, 14120 for guards, and so on. And then the C-type standards look at machine specifics. So there, for example, will be 10218 for robots, 415 for various different types of packaging machinery, etc. Now, 14119 is for all general aspects, so it's a B-type standard, so it sits in that middle grouping there. And if we take some details that we can see from 12100, so once we've commenced the risk assessment and we've looked at the various sections and we've realized that there is some sort of risk reduction measure that's required, there is a hierarchical three-step process of going through how we can do that. So initially we would try and design it out. So we'd change the whole design if possible to get rid of any risk or hazard. If that's not possible due to the nature and the type of what the machine is and needs to do, then we will look at safeguarding and complementary measures. And this is where 14119 will sit along with the various other B-type and, if applicable, C-type standards. So that's where it sort of fits into the structure. But the standard itself is titled Safety of Machinery, Interlocking Devices Associated with Guards, Principles for Design and Selection. And this is particularly 2024 edition. On the 12th of March this year, the EC published the standard, and it's the a revised and updated third edition, and it will completely replace and repeal the second edition, which was last launched in 2013. So from now on, this is the version of the standard that you should be looking at for the projects and such that you're looking at for machinery interlocks. So it looks at specifying the principles for design and selection, and there basically will give us details of looking at any type of energy source, so it can be electrical, pneumatic, hydraulic, or whatever it is that we need to control. And it will give us details around the selection and application of the various parts of the guards and their actuators and their interlocks and how it's there. And also trapped key interlocking devices and the systems and things associated with them, which is one of the key new parts that has been included in this latest revision. So the main changes for this revision is that technical specification 19837 is now integrated in his Annex K, and that looks at what they call Type 5, the interlocking devices, and we'll explain a little bit more about the different types that are referenced in the standard as we go through this morning. So there's a whole section on trap key interlocking and things in there that are defined as well. Table 5, which has been used for what types of devices and how they can be applied, has been improved and renamed. Some additional bits in there. There is a whole new section on test procedures, and you'll see later on this is mainly for people that are designing interlocks rather than the application of them on machinery. And the technical report 24119 is now integrated into Annex J, and this is the bit that looks at things like fault masking, which again we'll talk a little bit about later on. So the standard itself is broken down into 10 main clauses, and they are in essence as was in the previous edition. So clause 1, the scope, so what does it actually cover? Clause 2 is the normative references, so it will make reference to things like 13849, 13857, 14120, so other B-type standards and things like that you've got in there. Clause 3 is the glossary of all the terms and the definitions and things that it uses there. Clause 4 is a new clause that's been added, and that outlines the symbols that it uses and the pictograms in there for things like trap key or actuator locked or unlocked and things like that. Clause 5 is your operating principles and typical forms of interlocking. We'll have a little bit of a run through of what that requirement is. 6 is the requirements of design installation with locking. Again, we'll talk about guard locking and things with a few slides and things that we'll look at. 7 is the selection of a device. 8 about how we can minimize defeat, which is obviously a key thing that we need to ensure in the designs that we've got. We'll talk a little bit about some of the requirements around the control system, and clause 10 is just information for use. It's basically things that are given by manufacturer of interlocks and things, and then the things that they need to include in their documentation packs, etc. If we look at the annexes that are in there, they're defined and there's some been added that are in there. So Annex A to D looks at type 1 to 4 devices. E gives us an example of guard locking devices. F on the application examples and things that we have. G, all about the motivation to defeat. H gives us some details about static forces and things that you need to ensure that you have to apply to open or turn a lock on a guard or something like that. And they're all informative. However, the 3 new annexes that are put in there are normative. So these are must do rather than shall do. I looked at test procedures. J is the evaluation of fault masking, and K is particularly for type 5 trap key interlock systems. And again, we'll talk a little bit more about these as we go through this morning. So I've been mentioning types and things like this. So there are various types of interlock. And you can see there that what was table 1, the small picture on the left-hand side, that's been revised and updated. It's now actually table 2 in the new version of the standard. And you can see at the bottom there, it's added and now includes type 5 mechanical trap key, be it coded with an indirect or direct monitoring system. So all these details are things that are in there and are new. And you'll notice that it's referenced in there as well with the annex of Annex K. So it gives us the details of what the different types and things are and basic examples of them. So when we select the type of device that we're looking at for the application, it can be an integral part or a separate unit of the interlocking device itself. The 5 types that are in there, as we've said, there's basically the 5 types. They're in no particular hierarchical order. You can choose the one that's most applicable and suitable for your application, or you could even mix and match. So you could have a hybrid consisting of a type 1 and a type 4 device, or whatever it may be. And also, depending on specific conditions, the interlocking guard can be designed so that once it's actually been closed again, it can give a command to initiate a machine function without the separate use of a start control. So in essence, what's termed as a control guard. So, but again, there are specific conditions and things that you have to ensure that you can meet in that type of application. We need to ensure that we consider all phases of the machine life cycle. So, you know, what and where is the intended use? Where is it going to be? What hazards are there that we're trying to control? What is the severity of any injury? So, what are the likely, you know, the repercussions of something that somebody might come into contact with a hazard? What is the probability of failure of their interlocking device? What is the overall stopping performance time and access time? Again, this is something where we need to look at where we may need to consider guard locking. And also, what performance level or SIL level are we trying to achieve? And type 4 interlocking devices gives us the means to avoid a single actuator being retaught in an unlimited manner. So we need to ensure that there is a specific process that needs to be followed and done to stop anybody just retraining actuators for type 4 devices so that they can be easily manipulated and overridden. So I spoke a little bit about, mentioned the fact that we may need to include guard locking, and this is around the overall stopping time or access for the machine. And we need to look at things like if we can open a guard and reach a moving part or a dangerous area or something like that, and so that it hasn't come to a standstill, for example, then we need to ensure that that doesn't happen. So we would therefore put some form of lock on the guard so that we can then refer to other sections within the standard, and we'll look at a couple of options on this later. But it means that we have some form of making the machine safe before we then unlock the guard to allow somebody to open it and get access. If basically you can open a guard and there is no hazard behind it because you've got immediate stopping or it's far enough away that things will come to a standstill before you can reach it, then we can have some sort of general interlock without guard locking. But again, if we look at clause 6 in the standard, it will give us a little bit more guidance and things like that that we have for this type of application. So I've mentioned types, and if we consider looking here at types 1 to 4, the picture on the left is for a type 1 device, or this will be something like cam operated little switch or something, the roller lever switch, whisker arm or something like that that comes along and will be actuated by a fixed actuator. Type 2 is a 2-part interlocking device, so where you'd have some sort of tongue or actuator that is inserted into the body of the switch itself. And type 3 and type 4 are where we have non-contact switches. So these are things like magnetic switches or RFID switches that can be coded or uncoded, that depend on that. But for all of these, we need to ensure that the switches and the position that they're in are reliable, removable only with tools. So we need properly fixed down and fitted switches. They need to be locked into position if they are an adjustable switch. We need to be in a position where we can prevent their disassembly, we can prevent their avoidance, so they're out of reach or hidden away or something like that. And we'll talk a little bit more about that when we come to a section later on. We need to protect them from external damage, so make sure that they're not going to be coming into contact with things that can damage the switch, and that their installation itself is correct, so we can follow the manufacturer's instructions on how and where it's intended to be fitted. The actuators, again, must be reliable and removable only with tools. We need to prevent their disassembly, so we shouldn't be able to take the actuator out of its fixings. And again, we protect them from external damage, so that they're not going to be broken and need to be changed and things like that that we have on any system. So that's types 1 to 4. We also have the inclusion now of type 5 track key interlocking style systems, and this is where you can see the types of images and things that it shows here is in clause 4. Remember I mentioned the section that's been added that shows us the different types of symbols for the various bits of things here. But in essence, it's where we have a 2-part switch and a separate actuator. And we'll talk a little bit more about these that when we go through into a section later on that looks more in track key systems. When using a track key system, and again, we'll talk a little bit about this when we talk later, there are various considerations that we need to make, and we can look at figure K13 in Annex K of the standard that looks at energy control. So it includes defining the type of energy to be controlled and stopping categories and the method of interlocking. We've got to consider the intermediate transfer, so anything that is arising from the stop category. So do we need some sort of timing function or something like that that we've got in there? And then consider access control. With things like this, it may be that we are looking at something where we've got a full body access. And again, we'll talk a little bit about this in a later slide. One thing to ensure that we are compliant with as well with this new standard as we move forward, and we have already presented some webinars and things on both this new machinery regulation that is coming into force 20th of January 2027, and it looks at various aspects of things that we need to take into account around security, both from an IT and an OT point of view. So we need to ensure that nobody can just dial into a machine, but also nobody can access a machine or get into areas that they may be able to access without having the right permissions and so on. And so I'm going to briefly mention here and just draw you to some of the little parts. But if we look at section 1.1.9, we've got protection against corruption, so we just need to have a thought around that. 1.3.7 is moving parts and protection against those mechanical hazards. And 1.6.2 is maintenance, or how we can access service points and things like that. So more than likely there'll be guards and interlocks needed to get into those areas. And we need to ensure, based on this new regulation that's coming into force, that we have some sort of control and security cover and of who accesses keys. So, for example, ISO technical report 22053 looks at anonymous keys, so things like trap keys and so on and things like that, and them not necessarily being allowed or meeting the requirements for the security control in the new standard. And also technical report 63074 talks again about security aspects for the whole set of standards around security, the 62443 series. But there are things available that can allow us to only ensure that interlocks and access points and things like this can be used by competent and authorized people by using various devices like authorization keys, tags, cards, tokens, etc. If we look a little bit about some of the details around technical report 22053, there are devices from Pilz. This is a Pilz webinar, so yes, you will see some Pilz devices in there. So there are things like our identification access management systems that have keys, cards, etc., to ensure that only authorized, identified people with the verification can actually get in or change a mode into a way where they can bypass an interlock for setup or something like that, whatever it might be, or again, get access into specific zones on machines to do certain tasks or functions that they may have there. So we need to be very, very careful in the selection of trap keys and what we're doing with these to ensure that we will be compliant with these future requirements in the machinery regulation. There are other areas that give us further advice and things like this. So we have technical report 63074 that gives us guidance on the application of the new security standards, in that we need to do a security risk assessment and things like this, which is an add-on to see who are we going to allow into guarded areas or give access to people to get into these. So it's just a reminder that there are other considerations and things. We're not going to go into any real detail on that today, but there is more things to consider with interlocking devices. We talked, or I mentioned briefly, there's a section that looks at defeating safeguards and avoiding manipulation of those. And it's quite interesting that BGIA, a German organisation, did a report a few years ago now, but the manipulation of safeguards on machinery. And it was found that over a third, so 37%, sorry, of safeguards are manipulated constantly or occasionally, which, I mean, that's an incredible amount of numbers. But 25% of all accidents were found to be attributed to operating machinery when manipulation had occurred. So somebody had bypassed a guard or an interlock or something like that to get into an area, and that is the ultimate reason why the accident occurred. So it's very important that we try and ensure wherever possible that we avoid people being able to manipulate, override the functions that have been designed on the machine. And if we look at figure 8 that you can see on the screen here from the standard, it talks about the measures and things that we have available to us that we can use to avoid manipulation and things, and how do we actually decide if we need to do it? So is there a motivation to defeat? Is it possible to eliminate it? You know, can we get around it? What can we do to stop people manipulating it, etc.? So there's a lot of considerations when choosing the device that we're going to actually use on the guard, depending on again the type and everything else that we select for it. So there are some basic simple things that we can do to prevent access. So we can mount it out of reach. We can have some sort of flange or shield or bracketry around it to prevent people from getting there, or we can hide it away completely if possible in the actual structure of the guard and things itself. We need to ensure that we can prevent the use of replacement actuators. So this is coding on type 1 to 4 switches, type 3 and 4 switches. And again, there are different levels of low, medium and high coding. We need to prevent the dismantling or the depositioning of the elements and things. So non-detachable fixings, making sure you have to use a tool and things like that. There's also some special additions that we need to look at in type 5 key applications. So you need to ensure that it's not possible to remove the key with a force less than 250 newtons. It must withstand a torque of 5 Newton meters when it's being turned, and you can't easily get a replacement, so you can't just nip down to the locksmith or knock one up in a workshop or something like that. But also have some form of how do you control the reordering of any spares or replacements and things like that that might be needed. There are details I mentioned at the beginning that table 5 had been updated, modified somewhat, things, and you can see in the red box there, for non-detachable fixings of the actuators for type 2, 3, and 4 and 5 devices, they are mandatory requirements that you have there. And now we've got the addition of the recommendations for the non-detachable fixing of the interlocking device. There are easy ways, basically, rather than having to jump through a million hoops and put all these different things and things on there. If we just take the option of having a high coded level switch, is a fairly simple option that gives us the presumption to avoid the requirements for defeat and things like that. But this table does give us further information if we need it, to ensure that we meet the requirements to try and minimize defeat. As I mentioned, there are different levels of coding on different devices. Pilz, for example, have different devices and different types of switches and things that we have there. So the mechanical range, the magnetic range, the hinge range are all low-level coding, 2-part actuators and things like that on mechanical devices and so on. The coded switches and things, the PCNCS range that we have different levels of coding. So we can, depending on what it is, it can either be a low, or if we have a fully or a unique coded device, then we can have a high level of coding. And then the more intelligent switches, the solenoid locking and electromagnetic locks and things like that that we have in there, again, have the options of different types of coding, and depending on the version, can achieve that high level of coding that you've got there. All of this interlock system and things that we choose within the application that we've got here has to be somehow or other controlled with the machine control system itself. And so we need to potentially look at the guard. The ideal thing that we would do is that whenever a guard is operated, it must initiate a stop command when opened. And it must also, whilst still open, prevent any unexpected or unintended startup. So the interlocking guards with guard locking must also be able to, in some way, release the guard lock, but only when we've got to a safe condition to allow that release to happen. And then again, when we open it, we've got to initiate the stop command and prevent an unexpected startup. And if we look at the requirements from 13849, the standard for safety-rated control systems, we need to ensure that whatever we've got will meet the required performance level for each of the safety functions. If it's PLE, then we need to ensure that we have a category 3 or category 4 architecture within the control system. Now, we can do that by use of a single PLE device, or it could be that we have multiple type 1, type 2 devices that give us that style of architecture and things that we've got in there. We can have systems that do a automatic self-check every time they're actually operated, and that helps us to ensure that we receive the correct level of diagnostic coverage for the performance level requirements. So it avoids the necessary requirement to have frequently operated checks to ensure that it just meets. But if we do have guards that are infrequently or seldomly operated, then we do need to ensure that we implement a manual test to ensure that it's still operating correctly. So it must be at least every 12 months for up to PLD with a category 3 or category 2 architecture. But if we have a PLE device, then it must be every month that we check that if it's not actually operated in that month anyway. The machine should give us some indication by way of some sort of visual display, also the HMI or a lamp or something like that, where we need to implement the control system. It can monitor the test and stop the machine if we either don't do the test or the test results in a failure. So it just forces the user to actually make sure that they implement that test on the required levels for the application that you've got. There are things that you consider around fault exclusion, and again, there are different things that you would need to take into consideration. They need to be assessed separately for the energy forms, so mechanical, hydraulic, pneumatic, electrical, etc. It needs to look at the whole mission time of the device, including any requirements that might be related to wear and tear over the course of its applications. And for PLE applications, it shall be dual channel or type category 4 style in its behavior or architecture. So type 1 devices, very basic, as we remember, sort of like roller plunger, whisker arm style devices or something like that. Fault exclusions shall not be applied to the mechanical parts. So that's a case of we can't take anything into account for that. And if we have PLE, then we need to have multiple devices and things, as we've said, to ensure that, that we can pick the faults up. Type 2 devices. So your 2-part mechanical interlock devices with actuators that go into the switch body housing. Any mechanical faults from damage or breaks of the actuator due to misalignment can't be excluded where we have additional alignment devices. Now, these are things that ensure that the angle of approach for the actuator into the switch and sort of limit end stops and things like that have been provided. That's a typical sort of additional alignment device. Those additional alignment devices must be able to withstand a load that's 2 times the expected operational force. So we need to ensure that we've got double strength stuff in there if we have some sort of additional alignment device. So it just ensures that the actuator will enter the switch body correctly. If it's on a large guard and there might be a bit of droop over time or something like that we've got there. If we can't exclude any mechanical faults and where PLD is required, then again, we need to look at the implementation of extra devices and things like that that's on there. But if we have a type 3 or a type 4 devices, the mechanical exclusion is only, the exclusion for the mechanical part is only applicable on the fastening of the switches and the actuators. And they should be in accordance with what the manufacturer has stated should be used to mount those devices anyway. If we consider fault exclusions for guard locking applications, then we need to consider the static forces and any bouncing that might be created for the sort of guards that could be slammed shut or something like that. So we need to consider damage or wear and tear of the bolt due to misalignment, again, if we have the misalignment devices fitted. Any breakage of the locking means is detected at the next operation of the guard, and it must initiate a stop command and not allow the system to be restored until that locking function, restarted until that locking function is restored. And breakages must be detected by the subsystem in line with the requirements of the particular performance level. For type 5 devices, then we need to look at what is generally considered to be single channel architecture for the mechanical parts. And in that case, it is very difficult to detect a fault. So we need to look at removal of any single point of failure or dangerous failure modes where it can be proven to be a possibility. Then we can basically over dimension things, so put heavier duty devices and things like that that's on there. But if we do that, again, this must be validated by either calculations or proof testing. You can design devices that have parts with intentionally weak points that would create a safe failure point. And there are devices on the market from Pilz and others that will allow you to do that. And also, just we need to consider that if we are looking at category 3 or category 4 applications, we have 2 interlocking devices so that the single channel devices achieve the relevant category behavior that's required from the control system. But single channel devices where faults are evaluated with no dangerous failures can also be used to achieve category 3 and 4 applications. We spoke about fault masking and the issues and things that arise around that. And this is something that basically has been brought in from what was the technical report 24119, technical specification 24119, is now implemented into the details of the full-blown standard itself. And it looks at things like the unintended resetting of faults or preventing the detection of faults in the control system by operating other parts of the control system. There are things that we need to consider, things like how many devices have we got connected in series, how frequently are they used, what are the distance between them, what's the accessibility to them, and the number of operators that we've got. And table J12 has been modified a little bit in this new version that talks about the probability of fault masking. And you'll see the section in the red box at the bottom that if it's foreseeable that fault masking will occur, so we do have multiple moving or multiple operating guards and things that can be opened at the same time, then in essence the fault masking probability is level 3. And in general, if it's FM or it's level 3, then it can be assumed that we have no diagnostic coverage. So again, that will have major consequences on the safety-related control system itself. So again, we need to ensure that we can put things in place to do that, to avoid that. So what is fault masking? How does it occur? And how is it possibly presentable? Well, you can see here in this application we have 3 guards, each with its own 2-channel switch connected in series back to a safety relay. So if we open the first guard, or guard number 1, but we have channel 2 has a defective means, or it has a failure of some point on there, then because we've opened the guard, channel 1's operated properly, that's fine, that's great, it'll stop the machine. So it initiates that stop command, and away we go. That's that. We can go in and do what we need to do. If we then close the guard, the way that the system architecture is that because it's not seen both channels change state, because we have a defective channel, a reset is prevented. So the machine is still in a safe state. It won't run, it won't start, because it's detected that fault. However, if you can open guard 3, for example, in this case, and both channels operate, so they've changed state, you in essence, when closing the guard, will reset the safety relay, enable the machine to be reset, but you have in essence masked the fault on the faulty contact on the second channel of guard number 1. It then means that if, for whatever reason, the second channel on that guard number 1 switch fails, it might be there's water ingress because it's in a washdown area or something like that, or whatever it might be. We then have an issue where if both fail, you open the guard and we lose the safety function. So fault masking is a very, very important thing. We need to ensure that we have a way of preventing this from happening. So again, if it's multiple guards that can be operated at any one time, this situation can arise where we can mask or not detect a dangerous failure. So how can we overcome that? What can we do to stop that from happening or to detect it if it does happen? We could potentially individually wire all interlocks back into their safety relays, and you can use things like the Pinos Sigma or Micronaut systems, so typical hardwired systems that are available from Pilz, or you could go into a programmable system, a system like the Pinos Multi 2, where you can have some sort of logic control and things in this software within that will allow you again to do different things with different guards at different types, depending on whether they're operated or not, but again can allow you to have multiple inputs onto one safety controller. Or it could be that you look at using an intelligent switch, I'll say, and this can be anything up to and including performance level E, where the device itself uses OSSD style outputs that perform a self-check every time it's operated. So, for example, things like working from left to right across there, we've got a solenoid lock with a bistable solenoid, so it's pulse to lock, pulse to unlock. We've got the S-gate system, which is a full gate control system, again, with solenoid locking and things in there. The S-lock, which is the electromagnetic lock, and the small little simple coded switches in 3 different sizes and things that are available. Talking of size, Pilz also produced the world's smallest RFID actuator. You can see it right on the very left there. It's just almost the size of a button, basically, that you can have on there. But all of these devices have self-checking functionality. They have RFID details in there, so they can be used as the Type 3, Type 4 devices and things like that. And because they self-check, we can series connect them, and we will not have the issue with the potential for fault masking and things that we have in the system there. One other point that I will mention just to consider is that if you have multiple switches connected in series, you do need to consider the reaction time of the whole system. So, for example, here we've got a system with a safety relay and 4 devices connected to it. Because of the delay between each switch and the cables and things going through and the reaction time of the safety relay, here we could have a worst case scenario of a reaction time of 340 milliseconds. So again, that needs to be taken into consideration on what is the safety distance that we need to have for where the guard is away from the hazard point. I mentioned there's a whole new section on test procedures, and this really boils down to people that are manufacturing interlocks. It's not so important really for users of interlocks really, but it defines both a locking force test and an impact resistance test. So we need to ensure, obviously, that the guard lock is mounted as per manufacturer's instructions. They look at the thing being initiated under full load. We know deformation in the guard. We need to repeat it 5 times on new and unused samples. And we look at the lowest value recorded and being classed as the maximum locking force. We also have the impact force test, which is when we are using the locking switch as a mechanical stop. So we don't have any other alignment additional facilities and features and put in there, like mechanical stops and things like that, to stop the guard as it comes to its closed position and hits the interlock. It basically boils down to taking into account test methods that come out of 60947 that have been used for a while, and details the bits that are in there. But as I say, this is more in line with the requirement that a manufacturer, for example, somebody like Pilz and things like that, will look at in the use of developing and designing their systems, and the information that is provided and specified as to what the limiting factors, etc., are for the applications that the user would then put it into. The final part really is the last annex that's been put in, and this is the section on trapped key interlocking systems. So we've all known for a while and used these, and there are various issues and things that we have associated with these, and there could be a simple key operated switch, it could be a bolt lock, it could be an access lock with some form of personnel keys, or it could be a key exchange system. So there could be a bank of keys that you have that, depending upon which gate you want to access, you've got to go through a certain process to release the right key for the guard that you want to get into. Ideal for use where multiple access points are, or where you need to switch off multiple energy or power sources. So we can ensure that access is only given once the energy is disconnected. We can, if needs be, put time delays in to ensure that they're locked until any stored energy gets dissipated. So we need to dump all the air or hydraulic pressure or something like that, or we remain with power on until a machine can get to a safe state. Each energy source can have its own key. Again, we need to prevent any unexpected startup with the use of the control systems, and there is a certain sequence to follow to ensure its correct operation. So generally, trap key interlock system relies on the transfer of keys between the switch, which might be on a control desk or something like that, and an access lock, which is a gate onto a machine or something like that. So you typically, they are separated, but they are functionally linked, and that function relies on the transfer of the key. The keys need to be coded to ensure that they only fit the corresponding device. As we said, there is a sequence of operation that is followed to ensure that we get the intended risk reductions. And keys should only be available once we've got the designated safe state. So we've switched off the power, we've dissipated any remaining energy sources, etc. There is in the standard a typical sequence that is given, that how the general systems would operate, and that would be based around, initially with the machine in operation, we operate the key which initiates the stop command. We then transfer the key from the switch to the lock. The key goes into the lock is then operated, which will unlock the system of the lock itself to allow access. Once we open that guard and we remove the actuator, it can trap the key in the access lock. And then what we would have is a reversal of that to put the machine back into operation. There may be, just on point 6, and we'll talk about it a little bit in a couple of slides, but it may be, if it's full body access, that you need to have a personnel key as well, so that you would leave the actuator key in there, but remove a personnel key from the access lock point to take into an area with you. We need to also, as we mentioned, these trap key systems have some form of key coding on there, so that if we have 2 or more of these devices with different safety functions in and around the same location, we don't want them to unintentionally share the same key. So we don't want to be able to access machine 2 with the key that's supposed to be used for machine 1. And it is crucial that we keep a register for these keys, so we know exactly which key operates which interlock, so that we can get the right one should we need a replacement or a spare or whatever it might be. We spoke about things that we need to control. This K13 chart I showed earlier in the presentation, and this looks at the various examples of things that we've got to control. So, for example, for energy control, we need to define the source of energy. What is it that we're trying to do? If it's electrical, we need to look at the stopping category. So do we need an instant stop or a timed stop before we remove the power? And what sort of interlock are we going to be using? Is it a control or power or valve interlocking and things that we've got there? So there's a whole section that we need to take into account of other things for just purely the energy control with a trap key system. We then have the intermediate transfer. So this is the taking the key out and putting in somewhere else. And so we need to look at the overall stopping time and define the requirements that is based on the stop category that's not covered by energy control. So do we need some form of time delay or standstill monitoring on there or something like that to get the machine into a safe state? We also need to look at how many different access points have we got. So how many keys are needed and how do we control that? And also, again, ensure that we have a correct operational sequence. So do we need to have some sort of initiation of a mechanical brake or a restraining device or chock locks put into any load that might be at a high level that you need to go underneath or something like that, for example. And finally, we need to consider the access control. And this is where we might have something like full body access. So we need a personnel key. So again, a further key exchange at the interlock device so that we can take that in there with us. We may also need to consider an escape release mechanism that needs to be applied on the inside of the lock. So should the gate actually close and lock behind somebody, then can we have some form of escape mechanism so people can force the lock open and get out of the dangerous situation? We need to look at the applied forces on these devices, so the locking force that's needed so that nobody can easily manipulate and override it. And also we need to define the authorization requirements, so only allowing authorized and approved personnel. So again, back to the security aspects and the details and requirements in the new machinery regulation that mean that we can only allow certain people to do certain things or access into certain areas. So that is all in the, as I say, the new Annex J, which is the additional bit that for trap key interlocking systems. And that, ladies and gents, brings me to the end of this morning's webinar. The standard you see there, 14119 2024 edition, is available and enforceable now, so you can work on that lot. As I say, it was March this year that became the latest version that was released. I have mentioned, obviously, other webinars and things that that Pilz do, and you can catch up on those on our dedicated webinar channel. There is all sorts of topics and things on there. Also, the pictures that you see on the left are from the Pilz website. You'll probably see on the landing page, if you scroll down, the top picture, and if you click the very top box on there that says Component Systems and Solutions, it will take you into an area with a virtual machine that you can see at the bottom, so you can see application examples and get information and data sheets and things like that from various needs for interlocking and control systems and things like that that are available from Pilz. At that point, there is nothing more really for me to say this morning, other than thank you very much for your time. I appreciate you registering and watching this webinar. I hope Jamie's been able to answer any questions that has arisen. If there are any outstanding, then we will get back to you early part of next week. It's a bank holiday weekend here in the UK, so I hope everybody enjoys the long weekend. And once again, thank you very much, and I look forward to seeing you on the next webinar.